gonna start with the eigenvalues, eigenfunctions. So what are they? For the boundary value problem, we look at the 2-point boundary value problems for the linear differential equations. And the parameter that I was talking about is the notation, like the lambda notation. Okay, so the goal is to find the lambda or the set of the lambda term or the parameter lambda here that give us the non-zero solutions. Okay, and that lambda is called the eigenvalue. From the German, eigen means proper. So we're going to look for the proper numbers that would give us the proper solution. So for each lambda, we're going to have multiple lambda options. So for each lambda, we get the solution, which is called the eigenfunction. So eigenvalue, eigenfunction. One eigenvalue give you one eigenfunction. So we're going to have the eigenfunction that associated with the eigenvalue lambda. So we're going to have like the set of the solutions based on the condition provided, which are the boundary conditions and also the pattern of the equation that we are solving. Okay, so the thing is, like in the equation that we normally see, we have like the second order and then the numbers everywhere, right? For this case, we're going to have the lambda appear in the equation, okay, with the conditions as you see the form of the the conditions here. Y, it could be y, both of them y, or one of them is y, the other one is y prime, but you're gonna have the condition at the two endpoints. So for this case, like one end is a 0, the other end is pi over 4. Okay, so from the boundary conditions provided, we will be able to find the particular solution and also find the specific term of the lambda or the eigenvalue that satisfy this equation with the boundary condition given. To work on it, same, it's more like I would say to solve this type of the problems, to solve as using the general guideline by looking for the associate auxiliary equation. Okay, like for this is still the constant coefficient because lambda is a real number. Okay, lambda is a real number. So to our goal is to find y, right? The goal is to find y, and part of the y that we're gonna get the eigenvalue, eigenfunctions for this problem. So starting with using the auxiliary equation that we normally do, the coefficient and the second order, that's the m squared, and this is the zero order, gonna be plus lambda. We usually have the number, right? So it's easier to solve for m. For this case, we just treat lambda as any real number. So for m squared plus lambda equals 0, we would get m as negative lambda on the other side, take the square root and then plus minus sign, right? If lambda is a number, well, no problem. We just did the same. We just do the same way as what we did in chapter 4. But this time, since lambda is parameter, we're gonna find the option that lambda will give us the non-trivial solution. Okay, gonna be 3 cases for the solutions of the auxiliary equation. As you recall, case number 1, you get the m1 not equal to m2, or both of them are real roots, right? The real solution. And case number 2, m1 equals m2. So this one is called repeated solution. Okay, repeated values of the m. And case number 3, m1 and 2, they are in the form of the conjugate complex, or the alpha plus minus beta I. Okay, this one is a conjugate complex. Okay, now we're gonna look at each case. Let's see what would be the option for the lambda that give us the non-trivial solution. For case 1, for case number 1, for the distinct real root. So I'm gonna write it as the 2 real root or 2 real solution. or the case at M1 not equal to M2, and both of them are real. For the case that you get the real number, that means the negative lambda has to be positive, right? Because the square root of positive, you're going to get the real number out. If the square root of negative, you're going to get the complex conjugate, which is the case number 3. So for case number 1, the term inside of the square root has to be positive, or we can say the lambda will be less than 0. Okay, and to get the real root, we're gonna introduce the new parameter or the helper, you know. So I'm gonna use the omega squared, or let omega squared be negative lambda. Because the negative lambda is positive, so omega squared gonna be positive. That's our goal, just for our convenience to solve the problem. If the omega squared greater than 0 represent a negative lambda, that means the m gonna be plus minus square root of omega squared, or just plus minus omega. Okay, and then from this, we can use it to put together as a general solution. So the general solution is, this is about y. So y equals the C1 e to the omega x plus C2 e to the negative omega x. Okay, as the same pattern of what you did in chapter 4. And then from the two conditions provided, y at 0 equals 0, y at pi over 4 equals 0. From the y at 0 equals 0 and y at pi over 4 equals 0, we're going to use these two conditions to find C1 and C2. Okay. And we don't have to find y prime because the conditions provided, they both are in the term of the y at two endpoints. So for x equals 0, we get y equals 0, e to the 0 is 1, so we have C1 plus C2, or C1 equals negative C2. Okay, set it aside. And then second condition, x equals pi over 4. X equals pi over 4, y is still 0. That gives us the C1 e to the omega times pi over 4 plus C2 e to the negative omega pi over 4. And from the relationship, the C1 equals negative C2, we can replace C1 with the negative C2 and factor the C2 out, okay, as negative e omega pi over 4 plus e to the negative omega pi over 4. Okay, and now how the next goal is to find out what is the C2, so then we can get the value C1 out. And with this factor, the C2 multiplied by e to the omega pi over 4 plus e to the negative omega pi over 4. This inside here is the real number that is not 0. Why is not 0? Because omega greater than 0, pi over 4 greater than 0. E to the power omega pi over 4 always greater than 0 by the nature of the exponential term. If you recall, it will not be 0, it just approaches 0, approaches infinity, or the negative power, it acts that the same way. Both of them, e to the negative omega pi over 4, e to the omega pi over 4, both of them positive, either decreasing way or increasing way. So then in the sum of these two will never be 0. That forces C2 to be 0. If C2 equals 0, so then C1 gonna be 0 as well. So for the case that the lambda less than, as we set up at the beginning here, the lambda less than 0, the solution is trivial. What does it mean? You're gonna get the solution like y equals 0, which not what we are looking for.